All right, so today we're going to talk about comparing proportions for two populations. So up until this point, we were just doing one population of people. Now we're going to compare. All right, so stem cell research was a pretty big deal when I was growing up to talk about it. People were really opposed to it when I was a child, and when I got into college, when we were it shifted a little bit about how people felt. So let's look at this problem. The researchers from the Pew study interviewed two random samples. Both samples, the one taken in 2002 and the one taken in 2009, had 1,500 people. In 2002, 645 people expressed support for stem cell research, and in 2009, 870 expressed support. Okay, so we're going to say that this is going to be the one we're comparing, P1, and we're comparing it with the old one, and we're going to call that P2. Okay, so what I want you to understand is what we care about is the successes, right? So the people who support stem cell research. So P2 is going to be 645 divided by 1,500. It's going to be a percentage, all right? And P1 is going to be the percentage of 870 divided by 1,500. But before I get into all these P's, because I will tell you guys there's a lot of P's in this lesson. Let's just go through the steps of hypothesis testing when you have two populations. So, and again, this is just guided notes. This is for you to take in the information. We're going to do two practice problems, and then tomorrow we're only going to do one or two problems, so it's not too overwhelming. And you can ask for support. And we're probably going to do this for this week and early next week. Okay, so we're easing into it because this is a little more challenging. So step one is coming up with your hypothesis. All right, and now listen. Your null hypothesis is going to be the same, that there was no change, that whatever happened, in the past stayed the same. That's always going to be your null hypothesis. But there can be three different types of alternative hypotheses. The two-sided, right, hypothesis, where we're saying that it is not equal, right? And we call it two-sided again because the normal curve has two tails, right? So the two proportions are different in the populations, right? So we're just saying they're not equal, right? Then the proportion in the population one is less than the proportion in population two, right? So in that one, what we care about is, the left side is less than, right? So that's the one we're looking to the left tail, and one-sided where we have a right tail, right? So and again, what switches is the size of the inequality. So in our example problem, I would have went with this, right? I wanted to see if it increased, but a lot of times, people go with the two-sided one. But to be honest, we're just doing the z statistic today, so I wouldn't worry too much about it. Step two are these four conditions for the normal curve. So, throughout the year, actually, we've been talking about the normal curve, and then there's these four conditions, right? And for here, we have to make sure we have a large sample, but it changes a little bit because we have two samples. So what you have to do is you have to make sure that the sample is, the number of successes are bigger than 10, and the number of failures are bigger than 10. And same thing with this one, that with the second sample, the number of successes are bigger than 10, and the number of failures are bigger than 10. And then we got to make sure it's random, independent, and then also independent within the samples. So the samples, like for example, 2002, 2009, they're independent of each other, right? There's no, we're not asking the same people. It's a different survey altogether. So, and in the question we even say that the conditions are met. So for step two, we're good. All right, here's the doozy, and again, this is for guided notes. So for this one, please pause and write down the notes. And for this one, please pause and write in all these new formulas. And they're not complicated. It's just that there's more of them. So first of all, our p hat, right, without the subscripts, this p hat is the total number of successes divided by the total sample size, right? So if you remember, I was telling you guys before that the total number of successes was 15, and the total number of of people who they sampled was 3,000. And when you put that in your calculator, you get that p hat is equal to 0.51. Okay, p1, that was in 2009. So total number of successes is 870 out of 1,500. And so when you put that in your calculator, you get 0.58. And P2 is in 2002, so that's 645 divided by 1,500, and so P2 is 43%. Right away we see, right, like the difference between P2 and P1, that's big, right? So we're going to assume the z-statistic is going to be pretty big. So now what we're going to do is we're going to take these numbers and we're going to just put it into our calculator, right? So I'm going to go to my Desmos and I'm going to put in, I'm going to do it from scratch so you guys can see it. So I'm going to hit AB, right? I'm going to hit 0.58 minus 0.43, all right? And then I have to do the square root, right, of 0.51 parentheses 1 minus 0.51. And some of you are like, how'd you get these numbers? I'm just reminding you, we got these numbers by figuring these three things out first. And how you do that is you just divide the numbers that they're talking about here, divided by the total sample size. And that's just how we do it. And then we multiply by AB 1 over, in the first sample, right, in 2009, we had 1,500 plus, in the second sample, we had also 1,500 in 2002. Okay. Close that parentheses. Look at that, 8.21, that's a huge z-statistic. All right, so now that's step 3, right, is we're going to write, let's put a new slide, a blank one. So now our z-statistic, right, is z equals 8.22. Right, that's pretty big. We know that if we put that into our p calculator for for either two-tailed or one-tailed, it's going to tell us that our p1 is bigger than our p2. Okay. All right. Let's do another problem. Foreman reported a study of patients with recurring chronic lymphatic leukemia. Okay, leukemia is the cancer of the blood. The study was randomized, double-blind, and placebo-controlled. So that right there is telling us that it is, it's going to meet our conditions, right? It's definitely random. It's definitely independent. So after 12 months, 101 of the 110 patients assigned the combination treatment of ideal were still alive, and 88 of the 110 patients assigned to placebo with RIT were still alive. Perform a hypothesis test to test whether those who take ideal have a better chance of surviving than those taking the placebo. Use a level of significance of 0.05. So what we're going to do is we're going to take our major things, right? So we're comparing our P1, which is all right, so we're going to take the first one is 101. That's going to be our P1, 101 out of 110. and 88 out of 110. Okay, so I wonder if that makes it enough. So what we're going to do is we're going to go to our calculator. First, we have to, do our totals, right? So, all right, so we take AB, right, and we take 101 plus 88 out of 110 plus 110, right? So all our successes divided by the total sample size, we get a percentage of 0.86, right? And that's our p hat, right? That's just our p. Now let's do p1. P1 is 101, right? These are the people taking the drug. That's not 0.91. That's p1, 0.91. And now we got to do p2, which was 88, which is 0.8. All right, so now what I'm going to do is I'm going to take my two percentages. I'm going to subtract them. So I'm going to take 0.91 on the top minus 0.8. Now on the bottom, I'm doing the square root, right? And I'm doing my p hat, which is 0.86, and I'm multiplying it by its, its opposite, right? 1 minus 0.86, and I'm multiplying that by the reciprocal sample, right? The sample size, but when it's flipped. And all right, yeah. So 2.35, that's pretty good, right? So let's now what we're gonna do is we're gonna put it into our calculator. So p-value calculator from Z. All right. So if I go into my calculator, it was 2.35. And we want to see user level, can we conclude that ideal causes increased chance of survival? So we want to see if P1 is greater than P2. And, just in case, you want to double check, P1 is greater than P2, that's right-sided. So we go back to our calculator, we want to right tail, hit calculate, look at that p-value, 0.009. That's less than 0.05, right? So we can conclude, right? Let's use the language that we learned, right? We're gonna say here. Right. So we're gonna say that the p-value, first of all, the z is 2.35. All right, z equals 2.35. P is 0.009, right? And our P is less than our significance level, right? So based on the data, the null hypothesis can be rejected, right? Can be right. So we could say that based on the data, or if you want to be a little more specific, the data suggests that ideal, right, helps patients. We don't use strong language You know, yeah, I'm even thinking like I should double check if I can use this language can be rejected. But what we're doing is, right, the data suggests that, that ideal could help patients, right? That's the key, is always looking for that soft language, because in inferential statistics, we cannot be certain of everything, right? Okay, and just make sure you filled out your guided notes and turn it in, and thank you so much.